Really a pleasure to be back in Lincoln and see the marvelous changes that have occurred here on campus. And I see several familiar faces among the Nebraska section of APT members. Since we've all now have our brains working actively on a Saturday morning, which for me is not a normal activity, what we'll try to do this morning is introduce you to this subject of gravitational waves. You probably have all heard about this. There were Nobel Prizes awarded a couple of years ago for the first observations of gravitational waves. But first of all, remind you a little bit about why they're important and what we learned from them. And I got into this in a rather circuitous route, which I won't go into, but it's a basic example of how a scientific career can be very nonlinear. As Kevin mentioned, my previous work was really focused on atomic and molecular optical physics, laser spectroscopy, things like that, nonlinear dynamics. I did a little biophysics. And a few years ago, and at the end we have some time, I'll tell you how I got from all those fields into thinking about gravitational waves. And being a newcomer to that field, I never had any formal training in general relativity or any of that stuff. I just sort of stumbled on some things that were very puzzling to me. And it turns out, apparently there are some good reasons to be puzzled about this, and there's some results that have come out of these gravitational wave observations, which are really either pointing to some big mistake with the experimental apparatus that these people have been using, which I doubt very much. I've talked to a lot of people about how they calibrate their systems and so on, and it's all solid stuff. But results that seem to question some aspects of Einstein's general theory of relativity, which is really, if that pans out to be true, that's really a major upset in the way we think about gravitation. But maybe it's something more mundane. We don't know at this particular point. But that's just the kind of things that gets the blood flowing in every scientist, whether we're specialists in this area or not. So here's what we're going to do. I'll try to give you a little background. I'm assuming that most of the people in the audience are not experts in gravitational waves, but you all know some good physics and astronomy. So you have the underlying principles. Let's just gather them together to talk about gravitational waves. And then we're going to focus on one particular aspect of gravitational waves, what we call their polarization. And just to get your mind started in the right direction, just think of polarized light, linear polarization, circular polarization. It's that kind of framework that we're going to address, but in terms of gravitational waves, where things are a little bit different. And then talk about how we might go about determining what this polarization is for gravitational waves. And I'll explain why it's a critical feature that so far has not been fully tested. It's the one of the many aspects of general relativity that really hasn't been probed in any detail up to the last year or so. Then we'll look at one particular gravitational wave event. And in this LIGO-Virgo International Collaboration for Gravitational Waves, they label things with this cryptic-looking thing here in red. GW means gravitational wave. No surprise there. And then it's the year. This was 2017 in August. That's the 08 on the 17th. Okay? So that's how they label their events. I don't know what they do if they see more than one in a day, but they have to figure that out. So show how that particular event is so far the only one that allows us to make any definitive statements about gravitational wave polarization, and why there seems to be something not quite right going on there. And we'll talk about what some possibilities are there, and then talk about what comes next in the study of gravitational waves and how we might get this polarization issue settled ultimately. And then think ahead, why pursue gravitational waves? That may seem like some very esoteric corner of astrophysics, but it actually connects in with cosmology, nuclear physics, probably every other aspect of physics and astronomy gets linked in ultimately to gravitational waves. That's a new tool we have for understanding the universe around us. All right, so we've got some work. So first of all, we ought to ask the fundamental question, what is a gravitational wave? And if you read the popular literature about these things, all they say, in 1915, probably heard the story. Einstein developed his general theory of relativity, which is a theory of gravitation. And then the following year, he recognized that these things should have gravitational waves. And then it took another 60, 70, 80 years before that actually got played out. Turns out that history about gravitational waves is totally false. People were thinking about gravitational waves back in the late 1800s. There was a British physicist by the name of Oliver Heaviside who developed a lot of the theories of electricity and magnetism in the form that we use them today. The form that Maxwell developed was impossible to understand. But Heaviside figured out how to apply these things. And he in one of his articles, he said, well, you know, this sort of looks like electromagnetism in some, gravity looks like electromagnetism in some way. If we have electromagnetic waves, we should have gravitational waves. And he even said, well, they should probably travel the same speed as electromagnetic waves, and they might have these kinds of properties, but didn't pursue that very much. Then in the early 1900s, people followed up on that idea, and famous names in physics like Lorentz, Sommerfeld, Poincaré, they all dabbled around a little bit with this idea of gravitational waves. So it was not something that was totally surprising. And of course, even if you think of it naively enough, lots of aspects of electricity and magnetism, like Coulomb's law, the force goes as 1 over its inverse square of the distance between charges. What about Newton's law of gravity? 1 over r squared, the distance between masses. So there's a lot of similarities. And if you have electromagnetic waves, it seems natural that you would have gravitational waves. But nobody worked out the details, and partly because I think they did some estimates and found these things would be so weak that you never possibly see them. And then it took Einstein and his formalism in general relativity. He was the first to actually work this through to the generation. So Einstein played a crucial role, but he by no means the first to get involved with this stuff. And so the basic idea is, say you have a system like the moon and Earth. What keeps the moon in its orbit around the Earth? Gravity, okay. So imagine that you decided for some reason to shake the Earth around a little bit, okay? What would happen to the moon? Well, a little while later, it would shake around too, right? It took a little while for that disturbance in the gravitational field of moving the Earth around for the news to arrive at the moon, and then the moon would arrive, would oscillate around a little bit. So that is a gravitational wave disturbance. Now, we're not going to move the Earth like that, I hope. And the effect would be, for the usual motions of the Earth, it's a very feeble effect on the moon that you really don't notice at all. But the principle is sitting there right in front of you. Okay. So in Einstein's gravity, I like to use the term Einstein gravity rather than general relativity because it focuses our attention on the gravitation, which is really the key issue here. In Einstein gravity, Einstein gave us a different physical picture of gravitational interactions. Instead of thinking of the Earth exerting a force on the moon and the moon exerting a force on the Earth, Einstein said we should think of it in the following way. The Earth distorts space and time around it, and then the moon goes in an orbit through that curved space-time. So you take away the notion of force, and you substitute for it this curved space-time. Sounds nice. Calculations are awfully hard, right? But it's a different conceptual framework for thinking about gravitation, and it has some very strong advantages, which we won't go into. But that's the basic idea behind Einstein gravity. So in that kind of framework, the gravitational waves are then sort of disturbances in space-time geometry. That's kind of hard to think about, and those disturbances in the space-time geometry can propagate like a wave, and in Einstein's theory, they should in fact propagate at the same speed as electromagnetic waves. Okay? And so it's those undulations in this curved space-time are what we'll call gravitational waves. Right. how do you imagine curved space-time? Well, it's really hard to think about. It's hard enough to think about space-time in the first place. Curved space-time and oscillating space-time, really hard to think about. Here was one computer simulation which tries to imagine that you have some objects toward the center of that diagram that are doing something, some masses that are doing something funny, and then these sort of waves are going out from that. And you can see it's really rather complicated pattern. And of course, that's just sort of a representation of spatial things. It's space-time, which is supposed to be undulating. That's even harder to think about. So that's one attempt to take a look at that. We'll look at some others in just a moment. But so why are we so interested in gravitational waves? A bunch of physicists convinced the United States government to put up several $100 million to build some observatories to try to detect these gravitational waves. So you have to convince people that this is important. And here's one way of giving the pitch for why gravitational waves are important. If you can receive gravitational waves, these are emitted by masses that are jiggling around in various places in the universe. So it's a new way of sort of getting information about what's happening out in the universe. Traditionally, astronomers relied on visible light. You see starlight coming in, and we learned a lot about the stars and looking at the wavelengths that are present, the spectra in the stars. We get their chemical composition, so we learn a lot of stuff from visible light. And then there was radio astronomy, which Catherine will be telling you more about this afternoon, which really gave us another window on what's going on in the universe, because different kinds of objects emit radio waves compared to those which are emitting the visible light waves. And then you have X-rays and gamma rays and a whole bunch of other stuff, all of which give us different views of the universe. So in that framework, gravitational waves are yet another messenger coming to us from what's going on in the universe with its own characteristic signatures. And I'll tell you about some things you can see with gravitational waves you can't see otherwise. So it's a new window there. And it turns out it's ultimately connected to a lot of the stuff that occurred early in the universe, a big bang and inflation and things you probably have heard about. And as I have mentioned, I'll give you specific details in a moment, these gravitational waves have allowed us to see things we couldn't have seen with visible light at all. In fact, the first observations of these gravitational waves came from some objects that people suspected existed but never had any evidence that they were actually there, which is really kind of cool. And then the particular event we're going to focus on has to do with an event with objects called neutron stars, that are spiraling around and crashing into each other, which had never been seen before at all. So a whole bunch of new stuff has come out in very short order from the observation of gravitational waves. Okay, now we want to talk about, as I mentioned, this one aspect of gravitational waves, their so-called polarization. And again, I'm sure all of you are familiar with polarization for electromagnetic waves, linear, circular. That's a good framework to think about. It turns out the geometry is a little bit different for gravitational waves, and that gives us an interesting handle on Einstein's gravity that is not possible to get to through other mechanisms. And one way of thinking about it is that in electromagnetic polarization, we think about an electric field oscillating and it has a certain direction going this way or up and down this way, where you have circular polarization. And we think of it in terms of a vector, the vector associated with the electric field. And magnetic fields do the same thing. So it's a vector property. But in Einstein's gravity, you got fancier mathematics because you're dealing with this curved space-time. There you need a more complicated mathematical object, a tensor. And you can think of that as just a 4x4 matrix or something of that character. And we won't need to know the mathematical details, but just so you hear the appropriate language. So given that you're dealing with these tensors things, what does a gravitational wave polarization look like? Well, you detect this the way, at least in principle, you could do for electromagnetic waves. You see how in electromagnetic waves you can determine the polarization by seeing how electrical charges respond to the wave coming in. Some of you may be old enough to remember TV antennas that were mounted on rooftops with little arms sticking out, and you had to turn this thing around in the right direction for your local TV station. Sounds crazy, but people did this. And what you were, and you had it, and you're out there turning this, and, right. And so what you were doing is aligning the conductors in your antenna with the polarization of the electromagnetic waves that are coming to you from the TV station. So you had to get those lined up properly. So what does it look like for gravitational waves? Well, this LIGO-Virgo collaboration, LIGO is Laser Interferometer Gravitational Observatory, and Virgo is the Italian equivalent of that. So it's an international collaboration, and there are other places in the world developing these same kinds of observatories. They put pictures out like the one on the left. You have two objects that are supposed to be orbiting each other, and it turns out these orbiting binary objects are the sources of almost, well, as far as I know, all the gravitational waves that have been detected so far. They're still processing some data, but those are the ones that have been seen. And here's the picture they gave, and it looks like, you know, stuff on water and ripples going out on water. And that is, the physics is so wrong in that. I've talked to some of the LIGO people, and they say, yeah, we know it's wrong, but we just told some illustrator to make something that looked like waves, and that's what the illustrator came up with. But it's so far away from the real physics of Einstein. So if you want to detect this polarization, and you can see the motion of those masses on the right, it's not simple back and forth stuff. It's sort of wiggling around, and shows that the character of polarization for gravitational waves is different from the polarization of electromagnetic waves, at least according to Einstein's theory. So these are all computer simulations, not real data. But it gives you some sense of what that kind of oscillation looks like. And it's different from the kinds of polarization we associate with electromagnetic waves. And so then the question becomes, can we detect that kind of motion of masses and see whether Einstein's prediction for that kind of motion and polarization is correct, or maybe that's an aspect of the theory that general relativity or Einstein gravity doesn't quite get right. So why should we really care about this? There was a famous quote I found from Clifford Will, who is an astrophysicist, University of Florida, who has really been a person who's, I think, most comprehensively looked at tests of Einstein gravity over the years in all its different forms, and has some wonderful review papers which are quite understandable to people who are not experts in Einstein gravity, about what kinds of experiments have been done, how strong is the evidence for different kinds of different aspects of Einstein gravity, and so on. And in one of his papers in 2014, he has this distinct statement about gravitational wave polarization. And he pointed out that if anybody found a polarization that's different from Einstein gravity polarization, Einstein gravity is in deep, deep trouble. And this comes about because in Einstein gravity, as I mentioned before, there are two aspects. You have this curved space-time, and that tells how objects are supposed to move. And then the distribution of energy and mass is what determines how that curvature occurs. And Einstein's gravity has a definite mathematical connection between the properties of energy and mass and how it's distributed and how it's moving around, and gravity generally, and gravitational waves in particular. So if the gravitational waves aren't doing the right thing in terms of their polarization, that means Einstein's formulation of connecting this curved space-time to what masses are doing is not the right one. Okay. Sort of an intriguing idea. Now, we know that Einstein's theory of gravity does pass lots of tests, but those tests are not sensitive to that particular aspect of the theory. So that's a part that has not really been tested yet. Okay, so if we're going to go out and try to test this theory, we need to know what kind of alternatives there might be. And for these polarization things, as I mentioned, there's this so-called tensor model from Einstein gravity. There's a vector one, which gets built up a lot like electricity and magnetism. And I have been working with a fellow at the Texas A&M University, Anthony Svidzinsky, who contacted me when I started first writing about this. He contacted me. He said, "Oh, really interested in your stuff because I have a vector theory of gravity which passes all the standard tests of general relativity but predicts vector polarization for waves. Ooh, that's kind of interesting. So he and I have been collaborating on some papers to try to lay this out. There's also another mode called scalar polarization, and there's some alternative theories of gravity that have that kind of mode. Scalar means things just sort of don't have any directions, but they sort of go in and out without any particular directional characteristic for them. Or you could have some theory which mixes all three of those together. Just to see, this is sort of the play chart, of alternative theories of gravity and what kind of polarization they can have. And the sort of turquoise color indicates that that particular theory could support that particular type of polarization. And there, of course, there's a little industry out there of theorists who make alternative theories for gravity, right? Which, of course, is the way science ought to proceed. You can't assume that a particular theory is the absolute end line. And there are good reasons for believing that Einstein's gravity is not the end story because it doesn't work well with our other fundamental theory, quantum mechanics, quantum theory. So people have lots of other alternative theories, and you can see some allow vectors, tensor and scalars. Some are like Einstein up at the top is only the tensor part, and so on. There are lots of other players out there who are ready to test this. Let me just look at this very carefully. You don't have to pay any attention to the detailed math, but it tries to line up the analogy between electricity and magnetism and gravity. And in electromagnetic waves, you may remember way back when you studied these, some E&M course as junior or senior, you had currents and you had charges, and currents and charges doing the right things could make electromagnetic waves. That's all we have to remember. And then you would say, oh, now we're going to deal with gravity. So we'll replace charge with mass. We'll replace electrical current with mass current, which we also call momentum. Right? And you put those together, and you should be able to do the same kind of stuff. So I did a little paper in the American Journal of Physics about 2 years ago, a year and a half ago, which showed how you can actually do that. You can take that analogy, and you get a lot of the results about gravitational waves that come out of Einstein's theory. It takes a number of steps, but each step each one of you would recognize easily. But there are a lot of steps. Anyway, and in Einstein's theory, instead of those simple combinations of terms, you get some terrible looking 4x4 matrix, which this is a simple version of that. But it has some of the same ingredients. It has mass, and the u's are actually a form of a velocity. So things that sort of look like momentum, but then they get multiplied by other velocities. So it's a little more complicated. But that's basically what Einstein says should be happening. And you can also view that distinction in another way. And in fact, there was a really nice paper by two former UNL physics and astronomy faculty members, Bill Campbell and Tom Morgan, back in 1976, ancient history. But what they showed is, in appropriate circumstances, you could reformulate Einstein's theory of gravity so it looks much more like electricity and magnetism, with some distinct differences, of course. And people have been playing this out nowadays, and it really holds in very general ways. And they pointed out that for electromagnetic waves, again, things are vectors, so you could write the electric field as the sum of vectors indicating different polarization directions. And in general relativity, Einstein gravity, you have this tensor thing, that's the double arrow G on the left. And then it has products of vectors, which are ways you can build up tensors. So they showed it's a kind of a nice analogy. We're using the same geometric structures, these vectors, to build up tensors. And so there's kind of a nice analogy between the way general relativity does things and the way we do it in electricity and magnetism. Very nice paper. But that was 40 or 50 years before we actually saw gravitational waves. So given now we know why we want to look for gravitational waves and what we're going to look for in terms of their polarization, how do we actually go out and detect these gravitational waves? Why did it take almost 100 years from when Einstein had his version of gravitational waves to actually having gadgets which can measure these things? And the basic difficulty is that gravitational waves are weak, at least from any sources that we can imagine. Maybe someday we'll be surprised, but generally they're extremely weak. And so you have to have some apparatuses really, really sensitive. And if you remember back to that YouTube video, you saw those little masses moving around. They were moving relative to each other, being pushed in different directions by the gravitational wave. So the trick is to build some instrument which, to exceedingly high precision, can measure the relative position of some masses. Well, you can just hang two masses here, and I get my ruler out. But you make some estimates of what kind of precision you need, and you say, no way is that going to work. So you have to find some method of measuring those positions to high precision. In fact, if you make estimates, and Einstein himself made these estimates, and that's why he sort of almost gave up on gravitational waves. They were just going to be too weak. You never do this. But a typical relative shift in some masses due to gravitational waves occurs out in the 21st decimal place. Ooh. You measure that accurately in lab most of the time? Not quite. So this is going to be a challenge. But we also know that one of the best ways of seeing masses shift around are optical interferometers. We take optical light waves, have them interfere with each other, and look for shifts in interference patterns. And probably most of you have done that kind of Michelson interferometer experiment at some point in your careers. And people were saying, oh, it still sounds a little crazy. But with some high-powered engineering, some good lasers these days, some clever mechanical engineering to take away vibrations from other sources, this actually seems to work. So optical interferometers were decided upon as being the best method. There were some other attempts earlier on with vibrating aluminum cylinders at the University of Maryland, close to where I work. Those turned out not to be sensitive enough by many orders of magnitude, but it was a start. So these optical interferometers seem to be the best way to go. But even when you do some calculations about what you might see, it still seems it's obviously going to be a great challenge to make all of this work. The optical interferometers, which I'll show you in a moment, I'll show you some photographs, have interferometer arms 4 kilometers long. So light starts here, goes down 4 kilometers, hits a mirror, comes back, interferes with light that went off that way 4 kilometers and came back. Interference fringes set up, and you're going to look for shifts in those fringes. Okay, so how much shift might you expect to see? Well, again, given that change in position, this 10 to the minus 21 is estimated to be what we might need to look for. Take that, multiply that times 4 kilometers, and on Saturday morning I'll give you the answer. 4 times 10 to the minus 18 meters is the distance shift. That seems small, doesn't it? Well, if we think about other atomic scales, size of an atom, 10 to the minus 10 meters. How about the size of a nucleus? A few times 10 to the minus 15 meters. So we're going to be looking for shifts in mirrors whose positions change much less than the diameter of a proton, even. Whew. This sounds absolutely crazy. And I think when the people first proposed this, they said, everybody agreed, yeah, this is absolutely crazy. But with some prototypes that were built, and then thinking about how you might engineer this appropriately, I recognize, this is not outside the realm of what we might be able to pull off. So, money got acquired, and some interferometers were built. And what do they look like? This is the one in Louisiana. There are 2 in the United States that are active at the moment. One in Louisiana, one in the state of Washington. And you can see a central facility building down here in the corner. That's where all the lasers and stuff are. And then there's these long arms that go out. You can see the one in that particular direction. That's 4 kilometers long. Light beams come back, detectors and so on, fancy electronics and so on in that receiving station. So these things can be built, but you can imagine, and of course you want to have all this, the mirrors and so on, in a vacuum, so you don't have air molecules bumping them around. You want to have them physically isolated from vibrations. This is a fairly isolated area, but there's apparently a roadway over here on the right where logging trucks go by once in a while, and they tend to shake things. So you have to do a lot of mechanical engineering and optical engineering to make this work. And as I mentioned, there are now 3 active observatories. One in Japan will be coming online fairly soon, and there's several more planned, another one in Europe and another one in India. And it turns out it's going to have many of these scattered around the Earth in order to help sort out the properties of these gravitational waves. And I'll show you how that plays out. So we have one in Livingston, Louisiana, Hanford, Washington, where the old atomic bomb stuff used to be done, right? Fairly isolated site. And then there's another one near Pisa in Italy, which is not so isolated. And of course, those arms out there are not to scale. Just want to make sure you know that. But those are roughly the orientations of these things. So they're like your old TV antennas, and they're pointed in different directions to pick up different aspects of the gravitational waves as they come by. Another important feature to keep in mind as we go along, these things are built this ended up being a practical matter. They can be constructed to be sensitive enough, but only over a limited frequency range, roughly from maybe 30 hertz cycles per second up to maybe 400 or 500. So if you think about the wavelengths that are associated with those wavelengths are many, tens of kilometers. So you can think of these gravitational waves as a really long wavelength things. And here's my interferometer on, and this wave comes swooping over that and makes things move around. Okay? So we're thinking of things in that particular frequency range. And then that was mostly what you could engineer and build. There are plans to put some things out into space, and those can be configured to be sensitive to much lower frequencies. And that turns out, when you talk to astrophysicists about what might be generating gravitational waves out there, there's a few things in this frequency range we can see now, but there are a lot more things at much lower frequency stuff that we'd like to look at in the future. But that's what we have now. Okay. So this is just a diagram to remind you of what these interferometers look like. Light comes in from, here in this diagram, from the left, and it's a laser-driven kind of thing. There's a tilted plate there, a beam splitter, which sends some of the light off in one direction. Some of the light goes through toward another mirror in the other direction. Mirrors at the end send the light back. They hit the beam splitter, form an interference pattern, comes over here to a detector, which reads that out. Okay? So in principle, it's something that undergraduates could do, and you can try to build. Easy enough to build one of these things in your own lab. There's just some mirrors and a little flat table, but you're not going to get the kind of sensitivity you need here. But at least you can see the principle of that, and you can tap on the mirrors and see the optical fringes move. So the principle is easy to illustrate. These mirrors, to isolate them from vibrations from the surroundings, are mounted like pendula, with some very thin glass fibers holding these things up, and they're layered in various ways. This is a lot of mechanical engineering. And the mirrors that you're looking at, what they call a test mass, but the mirrors here at the bottom are the lowest thing on that. And then there are other things that damp out the vibrations that might work their way through the system. And they can position those mirrors with little actuators there to get them in a stable point, and then you're looking at deviations from that. So it's obviously high, and it took them 10 years to figure out how to do this right. The first versions didn't really work well at all. And every possible physical effect you can think of comes into here. The thermal fluctuations in those fibers which hold up the mirrors are enough to shake the mirrors. So you want to keep these things very, very well stabilized. One in Japan is going to have those things cooled to cryogenic temperatures to reduce that effect. And so practically everything that can go wrong does go wrong, and you have to have engineering to get around those things. So it's quite a tour de force in terms of just making these things operate. But they work. And that's quite amazing in its own right. And the fact they actually see something, of course, is even better. This is sort of a cartoonish view of, say, some source of gravitational waves. Again, not to scale. The things we see are hundreds of light years away, or thousands of light years, or millions or billions of light years away. Doesn't matter in astronomy. Millions, billions, it's all the same. But the important point of this is that if you have, say, 3 detectors or more, when a gravitational wave sweeps through there, you can use the relative times of arrival to back out the direction from which that wave came. Standard ranging stuff that people know how to do for a long time. And knowing where that the gravitational wave is coming from turns out to be really important for unraveling this polarization process. And that's why, even though there have been maybe a dozen, 15 of these gravitational events recorded, there are only 2 that have a 3 detector signal. And so there are only 2 that allow you to define that position relatively precisely, and one of them is not precise enough to answer the question, and so we're down to 1. And that's the one I'm going to be telling you about. Again, here's some photographs of what these things look like, and they're all, again, the same sort of central station where there are lasers and detectors and computers, and then long arms that go out to form the interferometer. Okay, so we're going to focus our attention on the type of system that generates gravitational waves that's been detected so far. That is, 2 masses orbiting around their common center of mass. We astrophysicists know, if you think about it for about 10 seconds, you recognize lots of other things might produce gravitational waves. Supernova, galaxies colliding with each other, you know, lots of stuff going on in the universe that have masses shaking around. And whenever masses shake around, gravitational waves are going to be emitted. But to get in the particular frequency range for which these observatories are sensitive, and to get signals that are strong enough to see, it turns out these binary orbiting objects are the candidates we are most likely to detect. And they're the only ones that have been detected so far. People have looked for other things but haven't seen anything yet. So you have this orbit of these 2 objects, and you can just use good old Newtonian mechanics by and large, at least to describe those orbits up to a point when they get going too fast, then relativity comes into play. And here, say this orbit is over here, the Earth is over there, so the gravitational waves we look at are going to come off at some angle, and that angle will turn out to be important in our analysis later on. So we take that angle between something that's perpendicular to the plane of the orbit, that's the direction of the orbital angular momentum, and the direction that you're viewing out toward the Earth. Okay. So what do we expect that signal to look like? Okay, well, it turns out it's a signal which has some interesting characteristics, and it's really helpful to have a signal that has interesting characteristics that you can then zoom in on when you're trying to find these gravitational wave signals. And just to give you some language, and I'll show you a simulation of how this calculation runs, these are called Chirp signals because they have a frequency which gradually increases with time, and an amplitude which gradually increases in time, and some bird chirps go that way. Something like that. Okay? Except gravitational waves are lower frequency. But that's the basic idea. So you know generically what the signal is going to look like. And it turns out with a little bit of math, which I'll just show you the results in a next slide. Again, at this level of approximation, it's not that difficult to actually carry out the analysis. And I have a kind of a tutorial article I put on the archive preprint server, which is set up in a way to guide, say, a junior or senior physics major through this calculation. And the calculation takes a while to go through, and a lot of steps along the way. And so it's set up as a kind of tutorial where you do chunks of it, I guess, probing questions, students both think about it. And a number of students have gone through this and emailed me with great suggestions for improving it. But if you have a student who's interested in taking a look at this, have them grab that tutorial. Should be somebody, a junior or senior, who's had a junior level electricity and magnetism course. But beyond that, you really don't need anything fancy. Forget general relativity. The title of the tutorial is Gravitational Waves Without General Relativity. And it sort of lays out how this goes. And it's set up really for students, or faculty too, for that matter, or teachers who want to go through this and just see what the basic physics is that goes into this and how this actually leads to formal expressions that are pretty close to what general relativity says. Not exactly the same, but very, very close. And so what you expect to see for these gravitational waves is this kind of chirp signal. And in the lower right-hand part, this is data from the very first observation of gravitational waves by these detectors. And you can see this thing oscillating. And in the LIGO-Virgo general relativity jargon, they call that the in spiral. You're spiraling in your orbit. These things eventually bang into each other. That's called the merger. That requires some general relativity or full nonlinear gravitational theory to describe. And then the combined object is asymmetric and vibrates a little bit, emits some more gravitational waves, and settles down to a spherical shape, and then stops. The gravitational waves stop. So you have this in spiral, merger, ring down. That's the kind of signature you look for. And in fact, the very first one turns out to be the strongest gravitational wave that they've detected so far. So they're really lucky. It has exactly that form. And this is conjectured to be black holes or very compact objects of some sort. Black holes are the most likely candidates, going around each other, merging into a single black hole. And notice that time scale over which that occurs. Few tenths of a second. And these things have masses 20 or 30 times the mass of the sun. This is just hard to imagine. Objects with that much mass, they're only 10 kilometers in diameter, but that much mass whirling around each other 60, 70 times per second, merging into this other black hole, and boom. But it also means your detection equipment has to be ready for very short events, right? So you better keep your eyes and ears open. And the LIGO-Virgo people have been really clever about ways of doing that. Okay, so let's move on. Just a little bit of math to show you it's not all that complicated. The top expression is how the rate of change of gravitational energy going out into these gravitational waves, how that depends on the stuff that's orbiting. And as you might expect, mass is involved. Newton's gravitational constant, capital G, it's got to be there, this is gravity. And then the other things that are important are the frequency with which these things are orbiting, that's the omega. R is the separation, R times omega is speed in the orbit, so how fast they're going counts. So if you want to have a strong gravitational wave, you need lots of mass. That's where the black hole thing comes in handy. And you need things going fast. So you might have black holes orbiting each other, but if they're going slowly enough, the gravitational waves are going to be pretty weak. You've got to catch them at that last death spiral as they zoom in, going really, really fast. And of course, other things appear there, like the speed of light, not surprising, too. So it's not, it's a bunch of symbols, but it's not all that complicated. And Kepler's law, one of our dear formulas in physics, it plays an integral part in all of this. And it links the orbital frequency to the separation of the masses, just as it does for planetary motion. Okay, now let us go on here quickly. Okay, so we're going to zoom in now on this particular event that I mentioned before. This one turns out to be not black holes orbiting each other, but neutron stars. And Catherine can be the expert on neutron stars, but they're basically stars that have collapsed to the point where they're very compact, again, dozens of kilometers across. They're called neutron stars because the protons and electrons have all sort of squeezed together to make neutrons. I mean, this is all, that's gross oversimplification, but the basic idea. So they're very compact objects, but they're not black holes in the general relativity sense. They're still squishy objects. And here are the actual signals from these observatories. And the LIGO-Virgo Collaboration has these online. You can download them. They're nice, simple files to take a look at. You and your students can take a look at them. And with this neutron star, it turns out that with a smaller mass, we get less gravitational energy loss. So the spiral process is slowed down over several seconds now rather than tenths of seconds, which turns out to be good. But here's some data over some tens of seconds. Does that look like, any of them look like gravitational wave signals? I can't see it, right? The Virgo one is a little less well engineered at the moment, much noisier. But even the Hanford and Livingston one, you can see there's stuff going up and down in the order of a second. It's kind of crazy. That's all mechanical, optical noise, electronic noise in the system. But we say, those guys should clean up their act. But if you look at the scale on that, and I put in 10 to the minus 18 up there, so these are still extremely small variations in the mirror separations that are occurring. They're down at the level about the size of a proton. That's really quite good, but it's not good enough. Yeah, you don't see the gravitational wave signal there. So we have to be clever. We have to do some digital signal processing to see what's going on. We've got to get rid of some of that noise. As I mentioned, the detectors really aim for this sort of 30 to 300 frequency range. So if you do some signal processing, to narrow down that frequency range, they call it bandpass filtering. Here's the Livingston signal I showed you before. And after you do that bandpassing, you get the stuff on the right. Those big spikes at the end are just some artificial artifacts of the digital signal processing. You just chop them off. You don't need it for that. The signal is supposed to be near the middle. So you stare at that again. Where's that chirp signal? Well, I don't quite see it. That's because it turns out it's still about a factor of 10 further down in the noise. So at that point, most of us would give up and try some other experiment. But with some clever signal processing, you can do that. And here's where you have to, knowing what the signal should look like helps you figure out what kind of processing will help you track that signal. So we know we're looking for something where the frequency of the oscillations of the waves increases relatively rapidly. And there's a way of focusing on that particular aspect. Okay. There we are. And it makes use of a technique which is not all that well known in physics, but in acoustics and radar processing and things like that. It's well known. You, at various intervals of time, you do an analysis of what frequencies are present in your signal at that point in time. Move to the next chunk of time, do the same thing, next chunk of time. You know, the magic word is Fourier analysis. That's all you need to know. It's a way of figuring out what frequencies are present. If you do that, you can see there's clearly something going on here where that frequency is increasing. Finally. And it turns out the same analysis can give you a rough measure of the amplitude. Turns out to be this 10 to the minus 22. So this is way down in the noise. But with clever signal processing, you can extract that and see it. They said, well, if this is really a gravitational wave, this is for the Livingston Observatory. We should also see this with Hanford. Oh, I might mention, just to be, I have it labeled here, but on the vertical scale, it's frequency, but in octave units. It turns out that's the way the processing happened to work. And the horizontal axis is just time in the signal recording. And you can see now it's spread over maybe 10 seconds instead of a tenth of a second which is a godsend in this analysis. So here's the same thing for the Hanford Observatory. It's a little noisier, but there's still clearly something rising up there on the right-hand side. And if you overlay it with the one on at Livingston, you have to shift it in time a little bit. Why do you have to shift it in time a little bit? Yeah, they're in different locations. It takes a little time for the waves to get from one to the other. Okay? That's good. It tells you you're looking at something that is not just common noise from something happening elsewhere. So have some confidence there. So let's move right along with this. When we go to analyze this, it turns out the geometry of the detectors are important. So you use some vectors to indicate that orientation. I'll use that little d for a detector orientation vector. And then this looks like an awful mess, but it's not actually that bad. It turns out that the signals can be described in terms of things that depend on a bunch of angles. That theta sub I is the orbital inclination angle I mentioned previously. And then there are a bunch of vectors. The W vectors have to do with the wave direction and the polarization. And the little d vectors are the ones that tell you how your wave is lining up with your antennas. And those are expressions, when you write them out, are things that should look familiar. Dot products or scalar products of vectors. So to implement this, all you have to do is calculate a lot of scalar products of vectors. Or you train your computer, better yet, to do it. You don't want to do this, but train your computer to do this. And so it turns out to isolate the polarization effects. And this happens to be for the vector polarization, the tensor polarization of Einstein gravity has the same kind of vectors, but in different combinations. And the scalar possibility I mentioned previously has another combination of these things. But if you take ratios of these things, everything like the amplitude and so on drops out, and you get information about the relative amplitudes of these signals, and that's enough to decide which polarization model is correct. Now, as I mentioned, this particular neutron event eliminates a lot of some ambiguity in the possibilities by giving us a precise location of this stuff in the sky. And that's because when neutron stars combine, they spew off all sorts of debris, which is really interesting in its own right. But amongst that are gamma rays, X-rays, optical stuff, and so on. And the gravitational wave observatories, once they recognized they were seeing this neutron star event, alerted optical electromagnetic astronomers throughout the world, get your telescopes looking over in this direction. Of course, most of them are recording things all over the place. So just look in your data record for this particular event. And it was recognized in the sky. I mean, there are little diagrams here where you can see little dots, which weren't there before, were there during the event, and then go away afterwards. So that was the spot right in the sky, determined to very high precision. Actually, the gamma rays, which were the first to be recorded, arrived about 1 second after the gravitational waves. Now, people said, oh, I mean, gravitational waves go faster than the speed of light. Well, it turns out that's not quite true. Electromagnetic radiation interacts with charges along the way, and there's a little bit of a dielectric constant and all that kind of stuff. It slows them down a little bit. But the trip for this particular event was something like 10 to the 17th seconds. You can work out how many years that was, a lot of years. And so you're seeing 1 second out of 10 to the 17th time difference. So these things are really traveling very close to the same speed, which is a good indicator that Einstein got that part of gravitational radiation correct. Okay, so then once we have that information, and I'll try to wrap this up in just a minute, we know where this thing is in the sky, and we're all set. We have all the information we need to know to figure out the polarization, because these different modes of polarization make slightly different predictions about these relative amplitudes and phase differences between the signals. And there's a method that my colleague at Texas A&M worked out to allow us to extract these things with pretty high precision. We don't need to go into the details of that. But basically, that calculation gives you the kind of data shown in these graphs If this theory is correct, you do an integral and plot the result as a function of the collection time for the data. And if everything's working properly, it should be straight lines. The slope of the straight lines are proportional to the relative amplitudes of the signals. You can measure those off. You see Livingston's a little bit stronger than Hanford. Hanford's stronger than Virgo. And you can also measure phase differences. So you've got all the stuff you need. And let's see whether it works. This is just a reminder about those geometric properties. So the way we decided to put these tests together, it makes a relatively complicated looking diagram, but let me just quickly parse it. What we're plotting in the horizontal axis is this orbital inclination angle, how the orbit is tilted relative to us. The vertical axis is what's called the polarization angle. So you might have a tilted orbit, but it could be tilted this way or that way, and that's the polarization orientation. And then the colors indicate the phase differences, in this case between Hanford and Livingston. Remember, our prediction was minus 160 degrees, minus 2 point some radians. So that's over in this left-hand side where the numbers are negative. And that sort of funny-looking shape in the middle outlined by black lines is where the theoretical predictions for those amplitude ratios, the strength of the signal at Hanford versus at Livingston or Virgo compared to Livingston, that's the region that they point to. And so if you get all of those converging, the right phase difference and the right amplitude, relative amplitudes, that says that this particular model describes what's going on with those waves. So the vector model works. So let's do the same thing for Einstein gravity. And here are the results. We find that Einstein gravity can't account for those relative amplitude ratios. So there's no little black line there. So it says the data do not support Einstein tensor polarization model. Okay, now it gets interesting. So let's try to wrap this up real quick. So why did the LIGO-Virgo people, they actually published a paper in which they said those results favor the Einstein model versus the vector model? Why could it be so different? In fact, by large numbers, there's a thing called Bayesian inference you can use to put some numbers to these model comparisons. We won't go into that, particularly on a Saturday morning. Here's what we think is going on. If you look at the raw data that comes from the Livingston Observatory signal, the top one, again, is one of these frequency versus time plots. And you can see a little bit of the up-swinging signal, our chirp signal. It's good. But nature was not very kind here. About a second before these neutron stars emerged, the Livingston signal had this bang. They don't know quite where it came from, but a gigantic noise spike. They think it might be something like a bird landing on the roof of the building. They see these from time to time, but they can't quite correlate it with anything. So you get this tremendous spike. They call it a glitch. Tremendous noise spike. So signal analysis say, well, we could sort of average that out. And they do that, and they also take out, you can see there's some noise at 60 hertz from power line frequencies, 180 hertz power line frequency harmonics. Take that out, and that's what appears at the bottom. So that doesn't look too bad. But if you look closely at that, this is an expanded version of that sort of thing. You can sort of see the swirping chirp thing going up. But there's some funny places. Look just to the right of 5 seconds. This is a blank. Nothing there. Look over here around 10 seconds. Nothing there. You look over around where I pointed where that noise glitch was. There's a little bit of stuff, but right in the middle of it, nothing there. And what we think, well, what I know is going on, what that point to the right, just of 5 seconds, is where the signal sweeps through 60 cycles per second. Okay? And so you're trying to eliminate noise at that.
Sure, so you eliminate.
And you eliminate your signal.
Oh, gotcha.
Okay. But if you're just interested in the swooping up, you can just sort of fit a curve through there fine, and that gives you the basic chirp signal. But if you're looking at the amplitude of that, which is the critical part for polarization, you're losing amplitude in those spots. And from what we can tell by looking at the LIGO-Virgo software, they did not correct for that effect. Trying to get them to fess up to that, but I haven't been able to get them. So what we think is happening is that the LIGO folks ended up with a number for the Livingston amplitude, which is too small because they had these gaps in there. And if you just look at the place where you don't have the gaps, which is what we did, you get a number on the right-hand side. And you put those two numbers in the calculations. We can reproduce what LIGO-Virgo claim, but we think the right answer is the one on the right. So we're trying to figure out what's going on there. So let's just quickly take what our conclusions are from this. What are the possibilities? One possibility, of course, would be the most dramatic. Einstein didn't get this right, and gravitational waves don't have the tensor polarization that he claimed. That would be really dramatic. But there could be problems in signal calibration. These things are complicated gadgets. They're continually being calibrated while they're running by putting little puffs of light on the mirrors. Let the few photons bounce off. That's enough to shake the mirrors. So that's going on. We don't think that's it. In the analysis, there's some fancy stuff that goes on in this Bayesian inference model that the LIGO people use, where they assume some distribution of parameters, and that could be biasing things. And they haven't yet published exactly what they're doing. There are also the possibility, as these gravitational waves come through the Earth, there's gravitational lensing by other masses in the way, and that sort of distorts the waves. You've probably all heard about gravitational lensing. You see little spots of stars that are behind a big mass and things like that. That could be happening a little bit with the gravitational waves, distorting things. We don't know. There's no evidence of it. That's a possibility. You might be able to, if you're a clever theorist, tweak general relativity to allow the vector polarization in. And some people are thinking about that. Or you may have to go to an alternative theory of the type I mentioned previously. So to sort this all out, we need a better neutron star event, which I have ordered that up from LIGO and Virgo. One that didn't have that noise glitch, and one where they think very carefully about noise removal and how that affects kinds of things. And they're also working on the equipment itself to lower the noise level so the noise subtraction will be much less obtrusive, and maybe nature will be generous and put the neutron stars closer to us so the signal will be stronger and less. So we'll see what happens. So, yeah, so let me stop there. I run over a couple of minutes in my excitement to tell you about this. But I think it's an intriguing story of how a very complicated experiment. The LIGO-Virgo Collaboration has about 1,000 people working in it. Now, some worry about the vacuum system, some worry about the lasers, some worry about the calibration, some worry about the mechanical stress. Others are doing calculations and doing the computer analysis. It's a vast team of people. And in that kind of environment, it's easy for little things to happen that not everybody is aware of. Something might be in the software. They did uncover a few glitches in their software that they corrected that didn't influence this kind of issue, but did influence other things. So that's a possibility. So there are lots of things that might go wrong, and maybe Einstein's theory is perfectly fine once we get the instruments tuned up. But we don't know. And maybe we're seeing some new physics out there, which would be really exciting too. So thank you very much for your attention. Pleasure meeting you.